Lesson 21, Standard Score. The standard score is a measure of position of a particular data value relative to all the other data. The standard score measures position by specifying the number of standard deviations a particular data value is from the mean. The population standard score for a particular data value, capital X of I, is given by the formula Z equals capital X of I minus mu sub x, all divided by sigma sub x. The sample standard score for a particular data value, lowercase x of I, is given by the formula T equals lowercase x sub I minus x bar, all divided by s sub x. The population standard score is denoted by the letter Z. The sample standard score is denoted by the letter T. This allows us to distinguish between standard scores that are calculated based off of population values or standard scores calculated based off of sample values. The xi represents the particular data value for which the standard score is calculated. So the value we plug into the formula for the x is the value that we're trying to find the position of on the standard score scale. Subtracting the mean gives the deviation for that particular data value. And dividing the deviation by the standard deviation standardizes the position. After calculating a standard score, the convention is to round off the result to the nearest hundredth. That is, we round off standard score calculations to 2 places after the decimal. And whenever possible, we always want to carry as many decimal places of accuracy that we can whenever calculating any result. We leave the rounding off to the very last step. But sometimes that's not always possible. So, in order to reduce round-off error, the quantities used to calculate the standard score need to be accurate to at least the nearest thousandth. That is, if we are going to use rounded off values for the mean or the standard deviation in the calculation of the standard score, we need to carry at least one more decimal place of accuracy than we need in the final answer in order to reduce that round-off error. So we need to carry at least 3 decimal places in our rounded off calculations for means and standard deviations when calculating standard scores so that we can round off that result to 2 places after the decimal. The standard score is a dimensionless quantity. That's because both the numerator and the denominator contain the same units. So if we're measuring a length, let's say in inches, or weights in pounds, the data values, x's, are in that same units. And the means and standard deviations are also in that same units. So the numerator will have the same units, whether it be inches or pounds, and the denominator has the same units, inches or pounds. So when you take the same unit divided by the same unit, that is, the same quantity divided by the same quantity, always equals 1. And 1 times any number always equals itself. So the standard score is a dimensionless quantity. This makes the standard score very useful in statistics, because this property of the standard score permits the comparison of the relative position of data values from different sources or with different units on the same standardized scale. That is, this standard score basically allows us to compare apples and oranges. By converting the different data values on different scales or from different sources into a common standard score scale, it allows us to make comparisons. So not only do we have to understand how to calculate the standard score, we also have to know how to describe and interpret the result. The description or interpretation of the standard score scale is the same whether we're dealing with population values or sample values. For instance, let's calculate the standard score for a data value that falls precisely at the mean. In the population sense, that would be a data value that equals mu sub x. In a sample sense, it would be a data value that equals x bar. So if we were to plug these mean values in for x into the standard score formula, we would get the following result. And the numerators would be the mean subtract the mean. And whenever you have the same number minus the same number, the result is always 0. And 0 divided by any standard deviation always equals 0. So data values that are positioned exactly at the mean always have a standard score of 0. So whenever you calculate a standard score for any type of data value, if the result is 0, we know that its position is precisely at the mean for all the other data values. Data values above the mean have a positive standard score because data values that are above the mean are bigger than the mean. And when you calculate the deviation by taking that x data value, which is larger, minus the mean, which is smaller, you always end up with a positive result or deviation. So data values that are positioned above the mean always have a positive standard score. Conversely, data values that fall below the mean always have a negative standard score. That's because data values that are below the mean are less than the mean. And when you take a data value x, which is smaller, subtract the mean, which is larger, smaller value minus larger value always leaves a negative difference. And so data values that are below the mean always have a negative standard score. So we could just look at the sign of the standard score and tell what position the data value is in. Positive standard score means that data value is positioned above the mean. Negative standard score values means the data value is positioned below the mean. So now let's try to find the position of a data value that is located exactly one standard deviation above the mean. In the population case, that would be the mean mu plus one standard deviation above the mean, sigma. In the sample case, it would be the mean x bar plus one standard deviation s. So data values that fall at this position can have their standard score calculated by plugging these values in for x in the standard score formula. The numerators have the mean and subtract the mean. So again, same number minus same number equals 0, leaving us with just a standard deviation in the numerator. And then dividing by a standard deviation, we have a same value divided by same value. The result we get is always 1. So data values that are positioned one standard deviation above the mean have a standard score value of +1. Data values that are positioned exactly one standard deviation below the mean mean that in the population case, you're at the mean mu, subtract one standard deviation sigma, or for a sample, that would be the mean x bar, subtract one standard deviation s. Plugging these data values to find their position on the standard score scale in the standard score formula gives this result, where again the numerator has the mean, subtract the mean, same value minus same value is 0. But because we were below the mean, here we have the negative standard deviation divided by the positive standard deviation. So same value divided by same value equals 1, and then the negative divided by positive gives us the -1. So data values that are positioned exactly one standard deviation below the mean have a -1 value on the standard score scale. So we can carry out this same concept for all the other positions, right? Because the standard score tells us the number of standard deviations a particular data value is from the mean. So if a particular data value falls 2 standard deviations below the mean, its standard score would be -2. But if a particular data value falls 2 standard deviations above the mean, its standard score would be +2. If the data value falls 3 standard deviations below the mean, its standard score would be -3. But if the position of a data value falls 3 standard deviations above the mean, its standard score would be +3. Standard scores can take on any real number value on this scale. Standard scores do not necessarily equal exactly whole numbers. So we could have standard scores of positive 1.835 or negative 0.267. Now, as we were learning the standard deviation in an earlier lesson, we found that that measures on average, how spread out the data values are from the mean. So if we look at the same concept on the standard score scale, which tells us the number of standard deviations a particular data value falls from the mean, 0 would mean the position of the mean, and the standard deviation would be each of these values of 1, 2, minus 1, minus 2. So because the standard deviation tells us the average spread, one standard deviation above the mean kind of puts us in the middle of the above the mean data values, and a second standard deviation puts you towards the end. So if you look around plus 2 on the standard score scale, that's typically where you'll find your highest data values. Same is true on the below the mean side. One standard deviation below the mean is -1 on the standard score scale, puts you about the middle of the below average group of data. A second standard deviation below the mean puts you at a standard score of -2, which would take you all the way towards the end of the data, and that's typically where you'll find the lowest data values. So usually all or nearly all of the data values fall within 2 standard deviations of the mean. So whenever a standard score is calculated for any particular type of data value, the result we get is typically always between the -2 and the +2. But this is something that is not necessarily true all the time. Sometimes data fall outside of the +2 or -2 on the standard score scale. Even though it can occur, this doesn't occur very often. So we do observe a data value with a standard score falling outside of the +2 and -2 on the standard score scale. We interpret that as an unusual result. So in statistics, it is considered unusual whenever data values fall 2 or more standard deviations from the mean. So unusual data values produce standard scores of -2 or lower, or +2 or higher. Unusual data values do occur. It just happens that their occurrence tends to be somewhat infrequent. That is, unusual data values occur a small proportion of the time. Extreme data values, or what we call outliers, are also unusual. They just happen to be extremely unusual. Although the criteria for identifying outliers in statistics is not universally defined, for the purposes of this lesson, any data value that falls 3 or more standard deviations from the mean is considered an outlier. Hence, outliers produce standard scores of either -3 or lower, or +3 or higher. So outliers are unusual because they do fall outside of the +2 or -2 range. It's just that we classify these unusually unusual data values that go even beyond the +2 and -2 to the extreme of beyond +3 or higher or -3 or lower. We classify those unusual values as outliers. Even though extreme data values or outliers occur very rarely, when they do occur, their impact on certain results can be significant. Consequently, it is important to identify the existence of outliers in any data set, since careful consideration must be given to the method used in analyzing the results. So whenever we find a particular data value that has a standard score of -3 or lower, or +3 or higher, we classify that as an outlier. Then we need to consider the types of statistics that we'll use to analyze results. For instance, we mentioned earlier, the mean being a balancing point, and the standard deviation, which uses the mean as its reference point, are sensitive to outliers. Therefore, if we have any outliers existing in a data set, we don't want to calculate the mean or standard deviation to represent central tendency and dispersion. Instead, we would use the median and median absolute deviation to measure central tendency and dispersion whenever we have data that involves outliers, because they are resistant to these extreme data values. Understanding the standard score scale permits the interpretation of the position of particular data values relative to all the other data. In addition to indicating if the position of a particular data value is relatively low, moderate, or high, it also discerns if one data value is positioned lower, about the same, or higher, relatively speaking, than another data value. So anytime the interest is to determine whether something is considered low, moderate, or high, or if when comparing different data values, and we want to know if one is positioned lower, about the same, or higher than the other, the standard score is the result we turn to help answer that question.